So far, right, you might have wondered, so if you study quantum mechanics, usually we start with wave-particle duality, right? Usually we start with what we call as wave-particle duality, okay? I don't know if anyone of you was surprised. Throughout this lecture, I never mentioned the word wave, okay? Never mentioned the name wave, or the term wave. I never talked about wave, okay? Even in the double slit experiment, I said that the electron is in both slits at the same time, okay? I didn't say that electron is a wave or anything, okay? Now, to think of electron as a wave is slightly problematic, right? Because it's true that there is some sort of wave going on there, but it's not a physical wave, right? What we measure always is a particle, okay? So, on the screen you always find a spot. When you find a particle, you always find one particle, right? So, when you measure, the electron is always a particle, okay? So, one way to look at it is, we have quantum mechanics as a logical framework, right? We can do the quantum mechanics of particles, we could do the quantum mechanics of waves or anything, right? So the way I have described it here, it's a quantum mechanics of particles, right? I have assumed that electrons are some sort of particles with definite positions when you measure them, all right? So these are particles, and we use the rules of quantum mechanics, including the principle of superposition, right? So instead of using the terminology of wave, I just assumed that just as the mathematics describes, the particle is actually in different places at the same time, right? So the state of the particle, right? It's here, it's everywhere, all right? It's everywhere at the same time. Right? I didn't have a wave thing, right? But why do we have this wave-particle duality kind of thing? I'll just explain it. Okay? If you take the momentum eigenvector and find the what do you say, the representation in coordinate basis, all right? This is what you will get. This is the momentum operator in position basis. Momentum eigenfunction position basis. Right? You can easily check this. You can see that this is an eigen function of the momentum operator. Right? H cross by I, dou by dou x acting on, dou by dou x acting on, this is the normalization factor, you can leave it, acting on e raised to I px by h cross. Alright. Okay. So you see that the momentum operator acting on this state gives you see that this, it's d by dx, so this p will come out, okay, h cross and I will cancel, this equal to p multiplied by e raised to I px by h cross. Okay. You see that the momentum operator acting on this function gives you momentum multiplied by the same function. So this is an eigen function of the momentum. Alright. So eigenfunction, by eigenfunction we mean wave functions representing eigenvectors, alright, or eigenvectors in coordinate basis. That's what we mean by eigenfunction. Okay. And so what we did now is we checked that this is actually an eigenfunction of the momentum so this is an eigenfunction corresponding to the momentum eigenvector. Right. In other words, this is the representation of momentum eigenvector in the coordinate basis. Right. Now, if you look at this, you see that this looks like a wave, all right? But we know that, what are these actually? What do we get here? These are expansion coefficients. Expansion coefficients. This means that if you want to expand the momentum eigenfunction, okay, if you want to expand the momentum eigenvector in terms of the coordinate basis, right? What you do is that you integrate this equal to, we'll have some psi p of x, I'll write it, okay, x dx, all right? And this expansion coefficient, these are these expansion coefficients, and this expansion coefficients is this thing, right? We represent the vectors or functions of vectors by their expansion coefficients in a particular basis, right? So these are basically the expansion coefficients, which by taking the square, by taking the complex, by taking the modulus square, you can find the probabilities. Okay. Now if you look at this thing, all right, this is also known as a free particle momentum eigenstates. Right, free particle solution. This is also a free particle solution. We won't go into the details there, but if you look at this momentum eigenvector in coordinate representation, you see that this looks like a wave. All right, it has the form of waves. Okay? If you expand this, you get cos px by h cross plus I sin px by h cross, and this is a wave like this. All right, if you draw only the real part, it's a wave like this. It's a plane wave. Right. So if you take this function corresponding to every x, you get a complex number. Right. If you draw only the real part, you get something like that. All right, a sine wave or a cosine wave. Okay. This is only the real part. Of course, there's imaginary part which I cannot draw here. Right. Now, if you look at this, you see that if x varies by a factor 2 pi h cross by p, it remains the same. Alright, you see that the displacement in the wave remains the same. Displacement in this function, or the function remains the same if you change x to x plus 2 pi h cross by p. That's how you calculate the wavelength, right? What's the wavelength? What's the wavelength? If this is the height, right? Wavelength, this distance is the wavelength, alright? It's the distance between points at the same phase. Distance between the points which are exactly at the same phase. So you see that if you add 2 pi h cross by p to this x, alright, this becomes, you know that this becomes e raised to I p x by h cross multiplied by e raised to 2 pi I, alright, and you get back the same thing because this is equal to 1. Right? So you see that this thing behaves like a wave with wavelength 2 pi h cross by p, alright, or if you put h cross equal to h by 2 pi, you will get h divided by p. Now you see that these are the probability amplitudes, okay? These are actually the probability amplitudes. So the wave is not a real wave, it's not any real wave, it's just that the expansion coefficients, alright, they show a wave-like pattern with a wavelength h by p. Of course this is important, but it doesn't mean that there is any real physical wave out there, alright? Because if you take a two-particle system, then this wave exists in 6 dimensions, okay? It's the configuration space. If it's a one particle system, the wave exists in 3 dimensions, it's fine. But if you take a 2 particle system, again you can construct a wave like this, but then that will exist in 6 dimensions. Okay, so it's not actually a real wave, it's not any real wave that exists in space. So it's not actually entirely right to talk about a wave particle duality, not in this framework, alright. Here we have assumed, the way I have described, we have assumed that electrons are particles, and we have used the quantum rules or the quantum framework to describe particles called electrons. Alright, this is one way of looking at it. Alright, now you can think of this expansion coefficient psi of x and say that alright, this looks like a wave, this wave is spread out like this, so you can call it as a wave. But you have to remember that this is not any real physical wave. These are just probability amplitudes showing a wave-like pattern. Okay. So if you just plot the probability, because corresponding to every point you have the probability, it is like this. These are just the set of probabilities or probability amplitudes to be precise. Okay. So it's not absolutely necessary that you think of a wave particle duality. You don't have to think of electron as a wave. Right? At least this framework does not force us to do that. I think it's more simple, it's more consistent to think of electron as a particle, and this framework is the quantum mechanics of particles. Now you can think of electron as a field, and then you will have to do a quantum mechanics of field, and we have the quantum mechanics of field. It's known as quantum field theory. Okay, but once you go to relativity, you see that considering electron as a particle is not entirely correct. You need to consider electron as a field. Okay? You assume that electron is a field that spread throughout all space. And then you can use the same quantum mechanical rule, the same quantum mechanical logic to describe fields, and then you will have a different theory called quantum field theory, right? But in this non-relativistic quantum mechanics, it's fine to think of electrons as particles, right? We are doing quantum mechanics of particles, and in this framework, particles just exist in different points at the same time, or different states at the same time. You don't have to talk about waves at all. Okay, but this relation is important. Okay? This relation is important. It has also physical. It has also physical importance, because this relation tells us about how the probabilities of finding the free electron in space are distributed. All right. This relation, actually, this wave particle duality thing, or it's normally called the de Broglie wavelength. Okay, de Broglie wavelength. Okay. So the de Broglie wave actually tells us that it's important that the probability amplitudes are distributed in this form. All right, it has experimental consequences, but it's not a real wave. All right, it's not a real wave. There is no wave. There is only particle. At least in this formalism, in the way I have described. Of course, you can think about wave particle duality also, but I think it's a bit confusing. You don't have to think about it as a wave.